how the brain organizes when you have patterns of sound. And in particular, we were studying the brain of rodents and trying to understand how different sound patterns organize the frequency representation from low to middle to high frequency maps in the brains of baby rodents. And one of the things that I was very interested in was trying to understand how the patterns of the natural environment, let's say the vocalizations of the environment that the rat pups were raised in, or just the natural sounds that they hear, how that shapes the structure of the brain. And one of the things we did was to try and experiment where we raised some of these rat pups in white noise, continuous white noise that was essentially masking all of those environmental sounds.
And what was the consequence of animals being raised in white noise environment?
Well, one of the things that we didn't expect, but we found, which is quite striking, is that there's this early period in brain development where we're very susceptible to the patterns that we hear or see. In neuroscience, we call this a critical period or a sensitive period. And we have this for our eyes, but we also have it for our ears. And one of the most striking examples of this is that any human can essentially grow up in a culture where they hear different speech sounds from one language to another. And it's like after a couple of years, you lose sensitivity to sounds that are not part of your native language, and you have high sensitivity for the languages of your native culture. And that's pretty extraordinary, that human brain has that flexibility, yet at the same time has that specialization for language. And so we were trying to think about how do we model this, for example, in rodents who obviously don't speak, but we're just understanding how sounds and environmental sounds modulate and organize the auditory cortex. And one of the things that we found that was quite striking was that if you basically mask environmental sounds from these rat pups, the critical period, this sensitive period where it's open to plasticity, it's open to change, it's open to reorganization, that window can stay open much, much longer. And in one way, it sounds like that's a good thing, but on the other hand, it's also a retardation. It's actually, it slowed the maturation of the auditory cortex. It was ready to close when these rat pups were really young, but by raising them in white noise, we found out that you could keep it open for months beyond the time period that it normally closes. And so I think one of the things it taught me was that it's not just about the genetic programming that specifies some of this sensitive period, but it's also a little bit about the nature of the sounds that we hear that help keep that window for the critical period open and closed. Well, I think that it's, from my perspective, it's really clear that those sounds that we are exposed to from the very earliest time, even in utero, in the womb, where the sound is hearing the mother or father or friends around while in the womb, actually will influence how these things organize. And so there's no question that the sounds that we hear are going to have some influence, and those sounds are going to structure the way that those neural networks actually lay down and will forever influence how you hear sounds. And speech and language is probably one of the most profound examples of that. Not yet. I think that what you're asking is a really important question because parents are using white noise generators almost universally now, and for good reasons. You know, it is hard to have kids up at night. I've got 3 kids of my own, and was very tempted to think about how to use some of these tools to just soothe them and get them to bed, especially when I was like so tired and exhausted. But I think that there is a cost, to think a little bit about, we're not exposed to continuous white noise naturally. There is a value to having really salient, structured sounds that are part of our natural environment to actually have the brain develop normally. So whether or not that has an impact, while you're sleeping, it's not clear. I don't think that those studies have been done. What was really clear was that if you raise these baby rats in continuous white noise, not super loud, but just enough to mask the environmental sounds, that was enough to keep the auditory cortex, the part of the brain that hears, in this really delayed state, which could essentially slow down the development and maturation of the brain. Well, I think part of it is that over time we develop sensitivity to the very specific speech sounds in a given language, and the sensitivity improves as we hear more and more and more of it. And then on the other hand, we lose sensitivity to other speech sounds at the same time. But as part of that process, we also have a selectivity, a gain, a specialization even for those sounds, even relative to noisy backgrounds and things like that. I tend to think about it like, what is the signal to noise ratio? And so the brain has its own ways of trying to increase that signal to noise ratio in order to make it more clear. Part of that is how we hear and how it lays down a foundation for that signal to noise ratio. And so you can imagine a child that's raised continuously in white noise would be really deprived of those kind of sounds that are really necessary for it to develop properly. So I think with regard to those tools for babies, I think we should study. We should try to understand this definitively. I think what we saw in rodents would tell us that there is potential, things that we should be concerned about. But again, it's not really clear if you're just using at night whether it has those effects.
I guess the critical question that a number of people are going to be asking is, did you decide to use a white noise machine or not to help keep any of your 3 children asleep?
Well, I think the short answer is no. I mean, I obviously did a lot of work thinking and work on this and thought about it carefully. But there are other kinds of noise, or I wouldn't even call it noise, other sounds that you can use that can be equally soothing to a baby. It's just that white noise has no structure, and what it's doing is essentially masking out all of the natural sounds. And I think the goal should really be about how do we replace that with other more natural sounds that structure the brain in the way that we want to be more healthy. In that earlier work during medical school, I was doing a lot of what we call neurophysiology, putting electrodes into the auditory cortex and understanding how the brain responds to sounds. And that's how we actually mapped out these things about the sensitivity to sensitive periods. That experience with Mike Merzenick and thinking about how plasticity is regulating the brain, in particular about how sound is represented by brain activity, was something that was really formative for me. And because I was a medical student, I was going back to my medical studies. It was that in combination with seeing some awake brain surgeries that our department is really well known for. One of my mentors, Mitch Berger, really pioneered these methods for taking care of patients with brain tumor and be able to do these surgeries safely by keeping patients awake and by mapping out language.
So they're talking and listening, and you're essentially in conversation with these patients while there's a portion of their skull removed, and you are stimulating or, in some cases, removing areas of their brain. Is that right?
That's exactly right. And the only thing off there is it's not essentially, it is just that. The only difference between the conversation that I might have with my patient who's undergoing awake brain surgery is that I can't see their face and they can't see my face. We actually have a sterile drape that actually separates the operating field, and they're looking and interacting with our neuropsychologist. But I can talk to them and they can hear my voice and vice versa. And it's a really, really important way of how we can protect some of those areas that are really critical for language, at the same time accomplish the mission of getting the seizures under control or getting a brain tumor removed.
And is that because occasionally you'll encounter a brain area, maybe you're stimulating or considering removing that brain area, and suddenly a patient will start stuttering or will have a hard time formulating a sentence? Is that essentially what you're looking for? You're looking for regions in which it is okay or not okay to probe.
Exactly. So the first thing that we do is that we use a small electrical stimulator to probe different parts of the areas that we think might be related and important for language or talking, or even movements of your arm and leg. That's what we call brain mapping. And we use a small electrical current that's delivered through a probe that we can just put at each spot. And the areas that we're really interested in are, of course, the areas that are right around the part that is pathological, the part that's injured, or the part that has a brain tumor that we want to remove. So we can apply that probe and transiently, meaning temporarily, activate it. So if you're stimulating the part of the brain that controls the hand will move. It will jerk. Sometimes a fist will be made, something like that. Other times, while someone is counting or just saying the days of the week, you can stimulate in a different area that stops their speech altogether. That's what we call speech arrest. Or if someone is looking at pictures and they're describing the pictures and you stimulate in a particular area, they stop speaking, or the words start coming out slurred, or they can't remember the name of the object that they're seeing in the picture. These are all things that we're listening really carefully while we apply that focal stimulation. That's what we call brain mapping.
What are some of the more surprising, or maybe even if you want to offer one of the more outrageous examples of things that people have suddenly done or failed to be able to do as a consequence of this brain mapping?
Well, I think the thing to me that has been the most striking is that, some of these areas you stimulate and altogether you can shut down someone's talking. So person says, I wanted to say it, but I couldn't get the words out. And even though I've seen this thousands of times now, it's still exciting every time that I see it, because it's exciting because you're seeing the brain. It's a physical organ. It's part of the body. Outside of the veins, on top of it, doesn't look like a machine. But when you do something like that and you focally change the way it works, and you see that because a person can't talk anymore, and they say, I know what I want to say, but I couldn't get the words out. You're confronted with this idea that organ is the basis of speech and language, and way beyond that, obviously, for all the other functions that we have for thinking and feeling our emotions, everything. So that to me is a constant reminder of, this really special thing that the brain does, was compute so many of the things that we do, and in particular in the area around speech and language, generating words, something that is really unique to our species, is just extraordinary to see. Again, even though I've seen it thousands of times, it's just having that connection, because it doesn't look like machine, but it is doing something that is quite complicated, precise, and remarkable. There are areas, for example, the orbital frontal cortex that we showed, that if you stimulate there, the orbital frontal cortex is a part of the brain that's above the eyes. That's why they call it orbital frontal, meaning it's above the eye or the orbit, and in the frontal lobe. And it's this area right in here. It has really complex functions. It's really important for learning and memory. But one of the things that we observed is when you stimulate there, people tended to have a reduction in their stress. And it was very much related to their state of being, meaning that if someone was already kind of feeling normal and you stimulate there, it didn't do much. But if someone was in a very anxious state, it actually relieved that. And then we've seen the corollary of that, which is true too, which is that there are other areas like the amygdala or parts of the insula that if you stimulate, you can cause an acute temporary anxiety, a nervous feeling. Or if you stimulate insula, people can have an acute feeling of disgust. So, the brain has different functions and these different nodes that help process the way we feel. Certainly, I think that to some degree, neuropsychiatric conditions reflect an imbalance of the electrical activities in these areas. One of the things that was something I will never forget was taking care of a young woman with uncontrolled seizures. We call that epilepsy. It's a medical condition where someone has uncontrolled electrical activity in the brain. Sometimes you can see that as convulsions, where people are shaking and lose consciousness. There are other kinds of seizures that people can have where they don't lose consciousness, but they can have experiences that just come out of nowhere. And it's just as a result of electrical activity coming from the brain.